I asked them, when we asked them if we wanted to make a project, I totally forgot that actually we met at the same time that I met John Rich for 2016. We were young for the master's program. And now they are, so what's the professors, assistant professor in Australia, and finishing this year. So this is a big success, not only from the CIMPA, but for this thank you very much for
Okay, so thanks a lot for joining still the last part of today's program. So I'm Raymart Lagunero, currently finishing my PhD at the University of Graz in Austria. And this work is like a summary of part 1 and part 2 of my dissertation, which I'm very happy to share with you. So it's focused on hydrolysis of lipids. So remember all the food that you eat, we eat during our breakfast, lunch, and snacks. So all of these things contain little bits of fats, which we call lipid droplets. So these are stored in our body. So the goal of my talk is to provide, establish at first mathematical modeling for lipolysis. Okay, so these are my supervisors, Clemens Spender from Graz and Thomas Appel from Munich in Germany. Okay, so let me start with a brief introduction. What do you mean by lipid hydrolysis? So, lipid hydrolysis, basically, or lipolysis, sometimes biochemists would call it lipolysis. So it is the process of breaking down the fats in the body. And of course, that's the layman's term of it. But if you look at the biomolecular level of it, there's a lot more to see. So, for example, a lipid droplet is composed of this substrate, which we call triglycerides. So triglycerides are stored inside these lipid droplets, and they are composed of a glycerol backbone. And with this glycerol, there are 3 fatty acids attached to it. So this is a pointer also. Yeah. So these 3 strings of fatty acids. What do we do with lipolysis basically? What does it do? Well, during times of starvation or high energy consuming activities like exercising and all, our body will access these stored fats in our body, and the body will degrade it into fatty acids. And fatty acids, as probably some of us know, these are the building blocks of, for example, ATP. ATP is adenosine triphosphate. It's a cellular energy for the body. Okay, so this lipolysis is composed of 3 coordinated steps. Well, simplified, let's say, because we have a linear process of degrading, let's say, TG, which denotes triglycerides. DG means triglycerides. These are glycerols plus 2 fatty acids. And then you have MGs, which are monoglycerols, glycerol plus 1 fatty acid, and finally the building block glycerol. So in details, you have this. So you have an enzyme called ATGL. ATGL is adenosine adipose triglyceride lipase, which performs the first step of degrading these stored fats. So it is activated by an activator called CGI58, but at the end of the day, it's the enzyme ATGL that will start all this process. So the breakdown of TGs, it will produce one molecule of the glyceride and the first free fatty acid. And then another enzyme which preferentially degrades these DGs will produce this monoglycerol and the second free fatty acid. And finally, the third enzyme, called the MGL, so monoglyceride lipase, this hydrolyzes the MGs, producing the third free fatty acid and the fundamental backbone glycerol. So it's a simplified process which was established sometime in 2014. And at the moment, we would like to understand further what really happens during hydrolysis, because there are several other processes along with lipolysis that occurs on the surface of a lipid droplet. Okay, so before we do that, we first look at a test model. So in this first test model, we consider, of course, this is an example of a lipid droplet. So this is a cytoplasmic image of a lipid droplet in the body. So you see here this very nice spherical shape, let's say 3D. And you have your mitochondrion and endoplasmic reticulum and some other parts of the cell. But what is important here is that the structure of a lipid droplet looks like this. So inside this lipid droplet is a reservoir of triglycerides. So you have a stock of triglycerides inside this droplet, and around the droplet are some layers of phospholipids. And so the enzymes then are attaching on the surface of this lipid droplet. Okay, so how do we model this? Well, this is our first time to model this process, and so we postulated a region which we call an active region. It's an annular region with a thickness delta. So delta here, one can think of it as the molecular reach of the ATGL, of the enzyme ATGL. So the enzyme will attach to the surface. It's going to attract the triglycerides from the reservoir going to near the surface. And so we said that, okay, all of the chemical reactions, all of the breakdowns, everything happens in a thin region, which we call the active region. So this we denote by omega 2, and of course you have omega 1 here, which denotes the reservoir region. And of course you have the interface gamma, and the boundary of our omega. Of course, omega here is the union of omega 1 and omega 2. And these are the concentrations of substrates and enzyme in this omega. Okay, so for this domain, we consider again a simplified chemical reaction network. It's a complex balance, but still a closed chemical reaction network in this domain. And here we have these concentrations in the reservoir region, and then these concentrations in the active region. So you have TGs in the reservoir, you have TGs in the active region. And there's this, let's say, reversible diffusion of the boundary at the interface. Mu here is diffusion constant, the same thing with nu. And I have a linear feedback here, which is a physiological shortcut, of course, again, in order to establish a robust numerical test case. We chose this to be linear in the end. And finally, this feedback, this is a degradation of PG to DGs with a reaction rate, let's call it F. But in the numerics that I will present, F here is the first order mechanism in kinetics. Why did we do what we did? The goal is to establish compute a positive equilibrium solution. Okay, so with this chemical network, you impose, of course, look at this reaction diffusion equations. So U denote concentrations of DGs in the reservoir, and V denotes concentrations of DGs in the reservoir, and so on. So we are considering also, of course, the diffusion of the involved substrates in the reservoir region and in the active region. And of course, other parameters here, I have, for example, D3 and D2, which are shown to be constant at the moment. And then I have a kappa, which is the linear feedback. And then rho W, which is the first order Michaelis-Menten. So it's just a linear term. Of course, this reaction diffusion system is coupled with some initial data. And we were able to prove, of course, well-posedness, which is existence, uniqueness, and continuous dependence of solutions to initial data for the parabolic system via classical theory. So we used the Numerical approximation. But for the elliptic system, we encountered a lot of issues because, for example, the associated linear form is not coercive. And so from the classical elliptic theory, you cannot use Lax-Wien theorem. And so what we did is to use a fixed point argument and the so-called entropy method, which uses the property of the parabolic system to prove well-posedness and to prove uniqueness of the elliptic problem. So we have a preprint of all of these results, which is uploaded to arXiv just recently. So if you are interested to see, you can check. And of course, we perform a lot of numerical simulations for this. So in this slide, I am showing the finite element solution for the elliptic problem. So you are basically solving this variational equation A equals 0 plus some conservation law. Okay, so one might think that, okay, isn't it that your solution will always be a trivial solution? Because I have something like AX equals 0. Well, as long as you impose a positive total mass in the system, your solution will always be positive non-trivial. So what happens here is that at the center of the reservoir region, you see high concentrations of triglycerides, and as you move away from the center, of course you will see decreasing concentrations. And for the triglycerides, so at the center of the lipid droplet, you have low concentrations. As you move towards the interface, you see increasing concentrations. And it's the same observation that you will see in the active region. So we have done some numerical analysis, like for example, error plots in the L2 norm and H1 norm, but I will not discuss it in this case. But at the moment, we have done so far a first PDE modeling of lipolysis. But we are not yet done with that because, again, we're using Michaelis-Menten and mass action law for transacylation. And, from the talk of Professor Annabelle in the first day, we've heard a lot of Michaelis-Menten. And so, mostly Michaelis-Menten reaction term works mostly with single substrate, single enzyme reactions. However, what we have here are 3 enzymes and 3 substrates. And not just that, we also have a so-called transesterification or transacylation of triglycerides. What happens in this transacylation or transesterification is that the same enzyme ATGL can grab two molecules of the glycerides. Remember, we have now 4 fatty acids. This can form one triglyceride, so 3 fatty acids, and one monoglyceride. And it is impossible to distinguish the two. So as soon as you produce the glycerides from hydrolysis, these triglycerides can be used by transacylation to produce again triglycerides and MGs. So this figure shows the action of the enzyme ATGL to the substrate DGs. So here we have we only have an ATGL reacting to DGs, and as I said earlier, this ATGL is activated by this activator CGI58, and as soon as you put CGI58 in your experiment, you will see this decreasing concentrations of DGs and increasing concentrations of DGs. So what does it mean? Well, it means that ATGL is also doing something with the triglycerides. Remember what breaks down triglycerides? What breaks down triglycerides are HSLs. But then we found out, this is just a recent one, last year, 2023, a paper with my supervisor and some colleagues, that ATGL can potentially change the machinery of the lipolytic process because of this another transesterification process happening. So these two processes occur at the same time on the surface of the lipid droplet, catalyzed by the same enzyme. And so it's a little bit complicated now to just use Michaelis-Menten and mass action law. But then what we did, therefore, is to look at deeper. So in hydrolysis, what you actually do is, well, this ATGL reacts with DG, producing this ATGL acid complex. So it's a complex. And then after this complex is produced, water, that's why it's hydrolysis, water reacts to this complex, releasing the fatty acid and then the enzyme. And so for DG transacylation, I have detailed here the process also. So ATGL again reacts with DGs, producing the complex, and then the complex grabs this DG and then creates a DG and then releases the ATGL. So with these chemical reaction networks, one can look at the mass action system, and we had exercises yesterday about constructing, writing the equations for a mass action system. And in my case, I have this. So this system, it's just an overview, and this system satisfies 3 conservation laws. So first, I have the enzyme conservation law. Of course, we know this already. You can easily see this. You don't even need to assume, because you can easily see that by just adding this ODE for A and this ODE for C. And you will see that the evolution of A plus C is 0. That means that concentrations of the ATGL and the complex is always constant for all time. And the same is true for the glycerol, which lives in the substrates DG, DG, and MG. So I have 3 conservation laws, and I was asking Professor Annabelle yesterday also about the Michaelis-Menten. And my question was, in order to obtain Michaelis-Menten, you always, the literature always use first the enzyme conservation law before performing a quasi-steady-state approximation. And we've done some quick numerics back then and found out that it should be this case and not the other way around, primarily because if you do the other way around, so perform a QSSA and then use the enzyme conservation law, that means that you are throwing away the mass of the complex in the system. And so it's not the same system anymore. And so what we do then is to follow how Kelly's method was done. We use the enzyme conservation law to arrive at these five ODEs for the substrates, complex, and the fatty acids. Okay. Now we proceed with the quasi-steady-state approximation. Well, the first challenge here is how do you non-dimensionalize your system. And non-dimensionalization is an art itself. You can non-dimensionalize the system whatever you want. And there are many ways to do this. For example, in Kelly's method, there are many ways to non-dimensionalize. But at the moment, we prefer to use this so-called pairwise balancing. And so you non-dimensionalize your concentrations according to these reference concentrations. So for the complex, I'm using the ATGL, initial ATGL. For the substrates, fatty acids, and H, which is the H2O concentration, I'm using the substrates initial data for PG. And then crucial also to non-dimensionalization and QSSA is the proper time reference. Normally what you do here is to look at a fast time scale and a slow time scale. So you have time scale separation, and so that means that your problem is a singular perturbation problem. And so with all this non-dimensionalization, choosing your time reference to this one, take note that my time reference here, this is a slow time scale, is basically the rate of how much you degrade triglycerides. And of course, in the QSSA, you have a small parameter epsilon. And in this case, we follow, for the meantime, the classical enzyme substrate ratio. We assume this to be small enough, so it's less than, it's close to 0. And with this, you obtain this, we call it a slow-fast system. So you have a fast variable here, which is the complex, and then the rest, Q3, Q2, Q1, and F, are your slow variables. And so what you do now is, of course, to perform a singular perturbation analysis. So you write your solutions as these Taylor series expansions. You have an epsilon here is to n. And well, normally the order 1 system will give you already nice approximations. If not, well, you can increase the order of your approximation. But at the moment, let me present this order 1 system. So the order 1 system will give you this ODE algebraic system. And from this algebraic equation, you can actually compute for C. You substitute C in all of these ODEs and arrive at this very nice reaction rates, which now incorporates all the reaction rates in the hydrolysis and in class acylation. So it's not let's say shocking to see, for example, in the numerator this hydrolysis term. So if you basically set G3, L2, G2, G1 to 0, you will have something like Q3 minus Q3 divided by Q3 plus some constant, which resembles your Michaelis method. But not just that, you also see here a quadratic term. which now represents your transacylation process. Remember, you grab two triglycerides to produce TG and MG. And so from yesterday's exercise, if you have a 2 here, your reaction term here will have something like square root. And of course, in the equation for Q2, you will see -2 to the square. And so on. So this is now a generalization of, maybe let's say Kelly-Symmetric plus mass function law with hydrolysis and transacylation. Okay, so in doing this, in performing this perturbation theory, of course, I assume that all of the things on the right-hand side are also of order 1, which is not really the case. You can see here there are a lot of unknown parameters which we do not know the order. But at the moment, we do not have enough information to what to say with these parameters. But what we know so far is that, for example, the process of creating TGs out of TGs plus FAs is biologically impossible, as well as this FA plus MG, this reversible process, this backward process of creating TG, is also not so strong. And so we know that these rates are small, but then we are not assuming that at the moment. Okay, so this is now your QSA, and hopefully I still have time. Finally, these are some numerics of the original slow fast and QSSA systems. This is for epsilon equals 1, so even for epsilon equals 1, you obtain a close enough approximation. But if you increase, for example, the parameter h, you obtain a better approximation to the slow fast system. Of course, what is this now? Of course, I have said the backward process of creating TGs, which is this G1, is not so strong. So if you reduce this by 1 order of magnitude, you obtain this approximation. And combining all the assumptions that we had, so H is 1 order higher, G1 is 1 order lower, and epsilon is 1 over 10. And you obtain this approximation. So at the moment, what we can say is that at least for the order 1 system, we have a nice approximative system for the slow fast. Okay, for the last 2 minutes, just a comment on the equilibrium states. You can compute for equilibrium states of original system. This will lead you to a lot of nonlinear equations, but at the end of the day, you cannot explicitly compute of these equilibrium points, but you are sure that the positive equilibrium points will always exist. It is due to this so-called deficiency 0 theorem, which says that whatever positive values you give to your rate constants, you will always have a positive equilibrium, and it is unique. This is for the original system, and of course, numerics would confirm that. Of course, as I said earlier, it is possible that you have this trivial solution, but we are excluding this primarily because we are imposing positive mass in the whole system. So as long as you have a positive mass, you should not have a trivial solution. But here the red dot represents the unique positive equilibrium. That's for your original system and for several parameters. And for the QSSA system, I used this theorem, again, it's called deficiency 1 theorem, but it is not enough. What will give you the unique existence of positive equilibria is the so-called efficiency 1 algorithm, which tells you that you cannot have multiple positive. So the efficiency 1 theorem already tells you that it is possible to obtain multiple positive steady states, but the efficiency 1 algorithm will tell you if you can have more than 1. And according to efficiency 1 algorithm, you cannot have more than 1, and so you should have 1 unique positive equilibrium. So you can solve again all this system non-linear, but you cannot get an explicit solution, but some phase portraits of Q2 and Q3, and finally a summary of what I said. So first, PDE modeling for lipolysis and transacylation. You have numerical discrimination, so we use Phoenix. It's a finite element computing software, which is, let's say, close to the free framework, which we have seen earlier. We also use GeoPTEs, which uses isogeometric analysis. It represents exactly circular geometries, because here we have circular geometries. And also some numerical simulations of a prototypical model for lipolysis and at the same time transacylation. So thanks a lot for listening. It's 10 seconds before dinner, so I'm happy to hear questions.